I just did that. So the next operation is that. So I'm not back to the has jobs condition
I
check.
see. Okay. Yep. Okay. We're still in it. We're still in the
We're-
first iteration.
So temporarily we're out of jobs, but we're not done with this iteration of the loop, so we could still have more to do. I kind of wanted to do a sum up of where this binary tree data structure fits in to, I think we had like an original goal of, this phone book app. Right.
Okay.
Do you remember this?
Yeah, I think
we had
so.
this, we were like saying, well, we have a phone book app and we wanted to be able to add an entry to it, whenever we want. And we want to be able to retrieve a person's phone number by their last name. And we had these multiple attempts. Actually, attempt one was like you just added new entries to the back of the array, and then you search the whole array. And that was not good enough because searching the whole array is big of n. And I said I wanted everything to be fast, right? I want both inserting things and retrieving things to be fast. And then we said that we will sort the array alphabetically by last name. But then the problem is when you try to insert new things into the array and keep it sorted, that's big O of n. So that also doesn't work. And then we had attempt 3, which was we're going to use a hash table that's going to use the last name of the person as the key.
Right.
And then we can use that to look up the phone number, and that will actually be fast in both cases. So that's sort of the first winner, because inserting a new entry is big of 1 on average, with a caveat, but looking up is also a big O of 1. But then I said, well, okay, it's still not good enough, because what if I want partial matching? Like, what if I want to be able to write the first 3 letters of the last name and still be able to look it up fast? And the hash table cannot do that. And that's what brought us to the binary search tree. So I just wanted to wrap that up.
Yes. Good tie-in to I had kind of not forgotten, but it's good to bring my mind back to that. That was the point of this.
Yeah, that's the whole point. That's how I tried to motivate the binary tree. So attempt number 4 of this thing, let's put it over here. Okay, so attempt 4, we're gonna build this phone book using a binary tree.
Okay.
So we're gonna use a binary search tree to store entries that contain last name and phone number.
Okay.
But we're gonna use the last name as the key of the tree, which means we're gonna, when we're doing comparisons while searching down the tree, or we're doing comparisons because we're trying to look for a spot to insert a new entry, we're going to compare the last name.
Okay.
So this means but yeah, to add insert new entries, use the PST insertion algorithm, and that's big O of log n.
Right.
and then search for exact match. You use the BST retrieve or search, I guess, algorithm, which is also big O log n. Partial search. How do we do partial search in a tree? We didn't actually talk about that, but intuitively it should be possible because we have this tree arranged in this sorted way, right? So maybe I should make room over here. Yeah, there's more room over here. So let's say I have Jenny, Jeff, okay, over here maybe is Kenny, Abby, what's between Jeff and
F.
Jenny?
So between F and N, G H, John, no, because no, it has to be J E.
I can move stuff around though. John. So John is gonna come after Jenny. Maybe. Okay. John would end up here. Then maybe Kenny can be over here. I think this. Maybe add a couple more. Or maybe I do. I add jam. That's another one. But jam would go here though. So maybe. What's the correct arrangement?
Would Jeff not be to the right of Jam if you put Jenny back at the top and Jeff back as the left child?
Oh yeah,
because E is after A, going off the second letter.
Maybe I just okay. Oh, I'll put. Oh, here's a question. If I put Jefferson, where does he belong? Would he be coming? Jefferson would be before Jenny, right? But after Jeff, probably.
Wait, F. Okay, so we're going off the third letter between F. F comes before N, so Jeff and Jefferson would be above Jenny.
Before, right?
Before, yeah, before, yeah. Sorry.
John, and I can put in Joan here, I think. I want to double check though, so I'm going to I'm gonna bring up a shell. Do I have Python in here? I will install Python really quick.
Okay. Yeah, this simple task of creating this small tree with names is such a concrete example of like, oh, this is such a good job for computers because it's so hard, even when it's like all the rules of organizing by names. It takes so much mental energy to be like, okay, wait, which name is where?
Yeah. So I want to see, like, is Jeff greater than Jefferson or the other way around?
Yeah.
No, Jeff is less than Jefferson.
Okay.
So we have it correct. And Jenny should be greater than Jefferson, I believe. So Jenny less than Jefferson should be false. because Jenny is greater than Jefferson. Okay, so this is the situation I want.
Okay.
Let's see. So I guess my thing about partial searching is I want to be there's a lot of J's. So if I type, I have a search box in my app, right? Last name. And then I'm typing in it and I type J. And then I want to see like a drop down, right?
Right.
That'll give me all the J's. I want to see a drop down. That'll give me like jam or in order, ideally.
Yeah.
Etc. But if I put JE, then I should be getting Jeff, Jefferson, and Jenny.
Yeah.
And if I type JO, I should be getting John and Joan. I guess technically Joan should come before John because Joan is to the left of John. So that's what we want to do, right? I think intuitively the binary search tree will allow me to do this, and not only that, it will allow me to do this efficiently.
Okay.
Because like if I were thinking about JE, because intuitively it's like how we move this bar and then we just the comb the tree from left to right like this. So intuitively, it's sort of like, I just need to do this scan operation until we hit the first thing that matches our JE prefix.
Yeah.
And then once we hit that, then we continue. And everything we hit that still matches JE, we will print it out. And then the first thing we hit that doesn't match JE, we'll stop right there. Right?
Right.
That's all we have to do. So so that there should be an algorithm that will allow me to do that.
Okay.
Let's try to sketch that out. That would be like a very cool code challenge as well. I think I wonder, like, and that's so practical too. I wonder if Lead Code has that. So what would be the maybe just do pseudocode. So we'll call this like maybe partial match search. How will we do this?
So I have a question in my mind. The visual that you just showed that we've gone over before, where you have the line and it's moving from the left to the right across the tree. I guess this kind of gets into the tree traversal, because my thought would have been, oh, well, we always start at the root of the tree and go down. We're not going left to right.
Yeah. Maybe we shouldn't do this one first. Maybe we should do the tree traversal and then come back to this partial.
I feel like there's information I don't have. That's like, how do you do this? Yeah.
Yeah, that's a good, because this is honestly, this is kind of advanced. So I'm gonna put a question mark. Like, this is where we're getting. This is our goal, right? This is like the ultimate. Where the whole point of, in a sense, the whole point of binary trees is we want to be able to do this. So stay tuned for next time. But let's instead of doing this. But this is such a cool problem. I really like this, and I haven't. Nobody has taught me how to do this. So like I think somebody should do that. But yeah, so instead of this partial match thing, let's go take a step back and say, all right, instead of trying to do a partial match, let's just traverse the entire tree. We want a tree traversal. So let me ask you how to do this. Use your problem solving. Put on your problem solving hat. So the first problem that I'm gonna pose to you is just print every element in the tree. I just want you to print every name in this tree. How would you do that?
Okay, so first, where my brain immediately goes is kind of this idea of how am I going to move through the tree? And because it's sort of two-sided, or not sort of, it is two-sided. It's like, okay, well, I have to start at the root, and then it seems like I could either go down one side, but we talked about before kind of working our way down and like choosing a path. So let's say, okay, so I want to go, I'll put a pin for just a minute on actually printing the names and just talk about getting to each of the names.
Yeah.
So we start at Jenny, we go to the left, and we arrive at Jeff. Now we have two possible paths we could go down, and we actually ultimately want to go down each. So what I'm wondering is, do we just choose one and then we arrive at Jam? But now I'm at the bottom. So do I have to start back at the top, remember the path I went, and then go a different path? Or can I, when I'm at the bottom, can I back up and go the opposite way? But then how do I have memory of like which way I went? Okay, I'm at Jam. If I hypothetically could get backwards and get to Jeff, I have to store somehow like, hey, I've already been here. So
Yes.
I've already been left. Now I have to go right.
So yeah. The word memory is very very important, and yeah, let's talk about that. How do you remember where you came from, essentially?
Would it be like some sort of data structure that's keeping breadcrumbs? Would I have something that's like, okay, like I started here and then I went here, and then slot three, place three?
Yes. So what would that data structure look like? So let's say let me try to illustrate this out.
Okay.
So basically, I mean, I'm sure you're gonna, whoops. Yes, I do want an arrow. That's true. Oh, no. Okay. Whoa. What happened? Okay.
A mind of its own.
Let's just call this like current.
Current. Okay.
Like I want a variable that's called current. I thought the arrow, whoa, it's a bent arrow. Okay. Oh, there we go. Yeah, that's what I want to see. So as let's say, and I like to be intentionally vague about what this algorithm or this code is going to look like. So so let's just say we have a variable called current.
Current.
And initially we're going to set current to root, right? So this is at the very beginning. We're going to do that, which is Jenny. And then later on, we're probably going to move current down the tree. Yeah, so the statement that does that probably will look something like, current equals root that left. Let's move this over here. Some other thing may have to happen. And then even later on, you will end up with that. And so there's probably a loop or some other mechanism that makes that process repeat. But then maybe at some point you realize you're at the leaf. So you're like, well, if root dot left is null, then what do you do? you are you gonna come back up to Jeff? Where is Jeff? How do you this is what you were talking about. How do you remember where you came from? How do you get back to Jeff here?
Yeah. Well, one option, and I'm pretty
How
sure
do
this is not the ultimate option that we want, but I'm just sort of talking through what comes to my mind. One option is that in addition to storing current, we store previous every time. But that, I mean, I don't really love that. It's just kind of working through how my brain's thinking through this. If we store previous every time, it doubles every, instead of just storing current and switching that, we have to switch current and previous. And we really only care about previous at the end. We don't care about previous. Let's say this was a great big huge tree with many, many layers. It's the only reason we're keeping up with previous is so that at the very end we can be like, okay, now I go back. But okay, also, as I say that.
So okay, let's say we're able to go back to previous. Let's
Okay.
just assume we can do that. Are we gonna do this? Are we gonna do this? And then we head back up to here. And then what? I guess the reason you want this is so that later on you can say current is equal to current. Oh, this should not be root. This current equals current. You want to be able to get to the right side, right? That's why you're coming back up. You want to be able to say current equals current dot right.
Correct.
Now,
and I guess I do have to do that over and over again. I have to do that for every layer to make sure I get every right side of every subtree. Yeah.
Yeah. But then, so let's say that happens.
Okay. So then I go.
And then at some point, well, at some point you need to come back up yet again. After you're done with the right side, and then maybe you're gonna do this again. After you've done the right side, maybe it's oh, this is clearly this is not gonna work, because if I nest the if statements, then I mean I can't have a number of nested statements that's the same as the height of the tree. That won't work.
Yeah.
Because
It's not the right solution.
The height of the tree is dynamic, so I can't. But let's say I could. If I could, then you're at Jefferson and you realize, oh, I've looked at both the left and the right side, and the right side is null. So I want to come back up to Jeff. So current equals previous, because previous is pointing to Jeff. But now I want to point out another problem, which is, well, Jeff is done with himself and all of his children. So we want to be able to go back up to Jenny. How do you do that?
Yeah, because we've lost that reference to the previous.
So do we need previous?
Right. Yes, we in this if we were working off of this method, we would need every level has to have its previous.
That's true. Every level, as if now when you say that every level has to have its own version of previous, like how can you get that? Can you get it? How do you make it so that at every level it can have its own previous variable, say, or it just have some way of storing its own version of previous?
It's like you need to create another tree on top of this tree that's storing all of the metadata that you're traversing.
It is very much that. That's true. That's true. Maybe so what would that other tree look like? It's actually what you're saying is very right. It's very right at a it's cool because mm, that connection is not often made. But when you say it, when you say that there's another tree that's mirroring this tree, um, what do you think that other tree is gonna look like? What is that other tree?
That I'm still thinking about,
Yeah.
but it's like, hmm, it's like every spot, and the more I think about it, the more I'm like, is it actually a separate tree, or do we need to modify the things that are stored in this tree? And I really don't know. I'm really brainstorming and thinking out loud here,
Oh,
because
okay.
it's like each
Modifying. So that's another avenue too.
two separate. I'm
that,
blending
that, that,
ideas now.
no. But they're all related because but yeah, you mentioned multiple ways. Like you like you have on the tip of your tongue um described like multiple ways uh that
Okay.
people have used to solve this problem. So there's not just one solution. Um, but yeah, like the one that involves maybe not modifying the tree exactly. There's a very simple way to solve this previous problem. Um, if we had only maintained a pointer that can allow a child to get at its parent, then that very simply solves everything. So like
Okay.
so um so like we so far we've said like the each node has a left and a right, right?
Right.
That implies that like you know we're pointing this way and we're pointing this way. But
This
but
is what you
so
talked about last week, I
yeah.
think. It's
Yeah,
like a
yeah, yeah.
double arrow.
The double arrow means yeah, well maybe Jeff can also point to Jenny too. Why not? So
Hmm.
and that's an implementation choice. This is not often done, but
Okay.
sometimes it is done. Like in a lot of UI frameworks, this is done, but I don't think React does this. But but the DOM does do this, which
Okay.
would enable you to say um, current equals current dot parent, and you immediately get back to your parent.
Yeah.
So that actually solves it very simply. I guess the thing that's the cost of doing this is while you're adding new nodes to the tree, you have to also make sure you maintain this parent link as correct. And also, I guess you use a little bit more memory to just store that link. It's not a lot, really. It's fine. I guess that there's another potential hazard is there's more room for you to make mistakes. Like you forgot to update the parent link, and now stuff is weird. That kind of thing. But
Yeah.
so um, so that is one way. But
Okay.
but let's say we're not gonna do it this way. If we didn't have this parent link to go back,
Then
how would you do it? So that that's that's sort of like how to get back up. So method number one is maintain a parent point. That's actually 2 and 3. There's more ways to do this.
Yeah.
Let's
And
see if you
that,
can come up with one of 2 for 3.
yeah, so I think the idea that I had when I was saying create a tree on top of this
Mm-hmm.
or modify this, all of my ideas were sort of centered around what we just talked about, though, was having each node having awareness of not only its children but its parent. So now that
Mm-hmm.
we've already sort of talked about that one, now I'm coming up short a little bit. I'm kind of like, okay,
Oh, okay.
what else can we do? To be perfectly honest, I'm still mulling it over.
Okay, so okay, so remember, like last time, I gave you like an illustration like this, where as we're
Yes.
moving down the tree, it's like there's a window or a frame that follows you through the algorithm, right?
Yes.
And I said that, well, you know, within every frame, you're allowed to have these variables, or like the variables that you choose. Like maybe it when you're we have current is Jenny. Maybe you can also have previous. In this case, is null when we're at the top. So let me delete this to not confuse us. So we could, if how do we, so like, yeah, if we move down the tree, then the current will become Jeff, let's say, and then previous will become Jenny. um and then yeah, so we move it down here. I guess down here we change current to Jam and previous to Jeff. And when we realize that Jam has no children, we move the frame back up. What is this mechanism of moving the frame back up? That depends on, I guess one way is just sort of like if I were down here and the current was Jam and previous is Jeff, I want to move back up.
Right.
Maybe I just do current equals previous, and then that will allow me to kind of move up, and which means Jeff is here.
But we still have the issue where we've lost our reference to Jeff's previous.
Yeah, we've lost Jenny. We have no way to get back to Jenny. So how can we get back to Jenny? That's the deep philosophical question.
And maybe it's building a new subtree that shows everything we've done. That's like we're at Jenny, and then before we move our pointer from Jenny to Jeff, we create an entry in the new breadcrumb tree.
Yeah. Let's call, great, breadcrumb. Let's have a variable called breadcrumb.
Okay.
And basically, breadcrumb initially. So we're gonna add a new variable called breadcrumb, and breadcrumb is actually gonna replace previous.
Yeah, we don't need that anymore. Yeah.
Yeah. So we're using breadcrumb, and so let's say we're at the beginning. Make some more room here. All right. Oops, my breadcrumb. All right. Breadcrumb initially is null, and initially current is Jenny, and we want to move down the frame to Jeff, and basically we're gonna put Jenny in the breadcrumb, and then we're gonna set current to Jeff, and then now the key is when we move down to Jam, make the current Jam. What do we need to do to the breadcrumb?
We need to add Jeff to it, but we need to model the relationship between Jam, Jeff, and Jenny.
Yeah, yeah.
So
The key is add.
Yes,
We add Jeff without removing Jenny. So breadcrumb should actually be an array.
Okay.
Or a queue of some sort, or it could be a linked list actually. But,
okay.
Yeah, but like if you're doing like high level language like JavaScript, just use an array is totally fine.
Okay.
So we have a breadcrumb which is and the breadcrumb is basically this the path you took down this tree thus far. That's what the breadcrumb is. So now given that, when you're down here and looking at Jam, and then you're done looking at Jam because Jam has no children, you move back up. You can just say, okay, I will set current back to Jeff, and then I'm gonna remove Jeff from the breadcrumb list, and now we're back to Jenny, and now we still have a reference to Jenny.
Yes.
Yep. So that is a very valid approach to doing this. And I actually quite like this. So yeah, so we're gonna look at Jeff, but now we're back to Jeff. We need to somehow remember that we have already done the left side of the current node, and now the next step is to do the right side of the current node, right?
Yeah, true.
So we somehow also need to remember that. How to remember it? Let me think. We could stick more information into the breadcrumb, possibly. Like, mm, mm,
Could we? Instead of just storing, well, no, that doesn't help because we've already deleted Jeff. But I was gonna say instead of just storing the reference like to Jenny or to Jeff inside the breadcrumb, could we store an object that's like the reference and also which children have already been traversed?
Yep. We could do this. Mm-hmm. So like
but then
Jenny,
we can't delete it. We can't delete Jeff when we get back up to Jeff. We still have to have the entry for Jeff there so we can say, hey, Jeff's left child has already been traversed.
Mm-hmm. There's another way. Let me think. So another way of storing these relationships. Let me think. I'm thinking another way is to like because when you're doing your left and then your right, it's sort of like their jobs. Like I need to do my left and then I need to do my right. And I could potentially use a queue to do, like, if I had a jobs array. And then maybe I can say like jobs dot push current jobs dot push current left, jobs dot push current right, and then just by doing pushing it to the job, and then later on I'm gonna process the job, and then just by processing the job, it will again do this thing, do the pushing of the left and right onto the job queue again, maybe.
Okay.
That's
So,
another idea. That way, this implicitly remembers the left and right for you, whereas before you had to like remember, oh, did I do the left yet? And now this maybe sort of uh we flattened it into this linear job array. Um, that's another idea.
so I have a question about that. So the jobs, I like this idea. It makes sense to me, but are we basically saying for every node we're on, like right now we're on Jeff, try to do the left job and the right job. And then eventually we'll get down to, okay, so let's say, okay, so we're on Jeff and we go to run current dot left. We get to jam. We try to do current dot left and current dot right for jam, but they're null. So we know, okay, we're at the end. But we're going to run that for every place we get to, and then some of them are just going to be null and they're going to be unnecessary. Is that kind of it? Like we know
Yeah.
every time we're checking for a left and a right.
Every time we're check, yeah, I mean maybe we could check if it's null, then we don't push it into the jobs. That's fine.
Okay.
So um so we let me think. Let me see if this works. So like jobs is a job queue.
Mhm.
And then while uh so the idea of the queue is we're just gonna push, we're gonna say like jobs dot push the root.
Okay.
um so while jobs while it has jobs, I'm gonna do
Okay.
pseudocode. While it has jobs, um I'm gonna do it like Python sort of. We're gonna sort of dequeue or pop job equals jobs dot pop.
Okay.
And then that just means like if we're talking about printing everything in
Mhm.
the tree, I'm just gonna
Yes.
print the job value. Assuming job is just a node in the tree, I'll print the jobs value, and then I'm gonna jobs dot push my left. I could do the check, I guess, for nulls, but I could also
Yeah. No need to
job
write it.
that right. But well, I could say here if um, well, yeah, okay. If job dot left, then I will push it. Job dot right, then I will push it. Does this work? Um, so okay, let's see what that would look like. So I have a so initially I'm here,
Mhm.
and then I push Jenny into jobs. So jobs equals Jenny, and then I'm like, and then while there's jobs, I'm gonna pop Jenny off and print Jenny.
Okay.
So maybe I have a log here that is the printed. I printed Jenny, and
Okay.
then now I'm gonna put Jenny's children onto this jobs array.
But aren't you out of your condition while has jobs? Because right now there's no job.
I'm still here. So I just did that. So the next operation is that. So I'm not back to the has jobs condition
I
check.
see. Okay. Yep. Okay. We're still in it. We're still in the
We're-
first iteration.
So temporarily we're out of jobs, but we're not done with this iteration of the loop, so we could still have more to do.
Gotcha.
And
Okay.
that's it's kind of hinging on that. So now we're gonna basically push Jeff and John into the job queue with these
Okay.
statements here. And then we get back here. Yeah, we have jobs. And then we're gonna pop John off and print John. Or maybe it's Jeff. I don't know. It depends on how the ordering of the pop. Doesn't matter too much right now. Because I didn't ask for a specific order. And then here is Jeff. So we printed Jeff, and we're gonna push Jeff's 2 children into the job queue.
Okay.
So that's gonna be Jam and Jefferson. And then we do this again.
We still have jobs. Okay.
Yeah, we still have jobs, and we're gonna take John off and print John. So John is off, and then we're gonna take John's children and add it to the queue. So that's Joan and Kenny. So Joan and Kenny go onto the queue, and then we go back here, and then we pop off the next job, which is Jam. And then we're gonna put Jam's children, but Jam has no children, so we skip these, and we go back here, and then we gonna print Jefferson and take him off. And we're gonna put Jefferson's children, but he has no children. So all the rest have no children. So we're just gonna keep going these 3 statements over and over again. So which just means we're gonna print Joan and Kenny at the end.
So it works. Yeah.
Yeah. So this works.
I like this method.
Yeah. So honestly, I wasn't sure until I just walked through it now. But I've done this in the past, but it's been a while. But so I mean, this is good because it's a very small algorithm. Like we just wrote like 8 lines or something, or 10 lines. And it can handle it. And it I guess the difference between the like how is this related to this breadcrumb idea that we came up with? It's sort of like we're not tracking our breadcrumb necessarily. It's more of like how do I answer the question you had of how do we get back to my parent? How does this algorithm handle that?
So it handles it instead of a breadcrumb. I wouldn't call it a breadcrumb. It's using like every spot we are in the tree, every node we end up landing on as we're moving down, we're putting that node on the to-do list. The jobs queue is like a to-do list. It's like we're adding it to this still needs to be processed, which is would be the whole point of breadcrumb.
So it's actually it's not that we're going back up the tree. It's just that as we're going down, we've put
We've captured.
we've snapshotted everything we need to do.
Yeah.
Beginning at the top into these these to-do items, which will later get processed. So we're not worried about losing them because we know it'll later be processed.
Exactly. Yeah. It's really good. I like this. The more I think about it, the more I'm just like, yes, this makes sense to me.
Good.
I feel like maybe there's a downside to this. Like there almost always is some negative, but right now I'm still like, I don't even see the downside to this. I guess we haven't really analyzed the performance of it, but it's
Okay. What is the big O of this algorithm relative to the number of elements that are in the tree?
yeah, I think okay, so it's the number of jobs that gets pushed is going to be the number of elements in the tree.
Yeah.
And that's the number of things. So is it in?
Yeah.
Yeah, so it's not incredibly performant. Yeah.
Can you do better than N?
I know it can be done. Right now I'm like, okay, how? How?
Why do you know it can be done?
Well, okay, I guess I should say I'm not saying it can be done using this method, but I guess I just have confidence that someone has come up with methods out there that are better than in. That's what I mean.
Because those computer science guys, they're pretty smart.
Exactly. And this is a pretty, common thing that has to be done. I'm just sure somebody has come up with a more performant way to do it.
Okay.
But maybe it's not this way. I mean, this way, I think I like it so much because it's very tidy and it just sort of makes sense. It's very intuitive. But yeah, big O of N is not very good. So
big O, well, okay. I would actually argue that in this case, you cannot do better than big O of N. And the reason is if you think about it, is kind of intuitive because I asked you to print every element in the tree. And
you did.
which by definition means if there were 10 elements in the tree, well, you have to print 10 things. If I double that, you would have to print 20 things. If I triple that, you would have to print 3 times as many things.
So it's inherently having to touch every.
Yeah.
Yeah, I see that point. I do.
Yeah. So in this case, N, big O of N is the best you can do. And there's actually no way you can improve on that, because if you improved on that, it means you're not touching everything in the tree. Okay. So this is good. This is good. Now, let me think. Now, okay. So now that we've solved this problem number 1, how much time do we have?
Not very much.
Oh, not very much.
To wrap up.
Okay. Yeah. Okay. Maybe I'll just. We solved the problem number 1, which is print every element in the tree. So problem number 2 is print every element in the tree in order.
Okay.
Every element in the tree in order. So
that means
which is that animation we did, which I want to go this direction.
Yeah.
So maybe we just stop there and we'll reflect on it, how that might be done, and we'll talk about it next time.
All right, the cliffhanger for next week's episode.
Yes.